In this lecture, we will see the plane waves in good dielectrics and the good conductors. So on the last lecture, we have just understand the what is loss tangent. So what do you mean by the good conductor and the good dielectrics? So we have seen that we have the loss tangent that tan theta equals to sigma over omega epsilon. So if this theta is large, then it will be considered to be a good conductor, and if it is theta is smaller, then it is considered to be a good dielectric. We have seen this ratio sigma over omega epsilon. If ratio is more than 1, then it will be a good conductor. If less than 1, then it will be a good dielectric. Okay. So now let's focus onto the good dielectric. That is, if we have sigma is much lesser than the omega epsilon. So the dielectric means sigma over omega epsilon will be less than 1. This is a condition here. So what will happen to the attenuation factor and the phase constant? So 1 over sigma square over omega square epsilon square equals to, you can use a Van Helmont theorem to expand this. So because this factor is less than 1, you can open it and you can stop it here at the second term. There will be higher terms, but you can ignore them because a square of a smaller value will also become much smaller. So this is a approximated value of this factor. So here more approximation is, you can just ignore this also and you will become 1. This is a coarse approximation and it is a less approximation towards a more accurate value. So generally we'll focus on this also and we can solve for this also. So now gamma is equals to the propagation constant in general given by alpha plus j beta, where alpha is the attenuation factor and beta is the phase constant. And we have obtained that alpha, it comes out to be omega epsilon under root this factor. Now for the good dielectric, this you can either approximate to be this whole as to be 1. This will approximate to be 1. We can consider to be this 1. So this factor 1, 1 minus 1 will give you 0. So the attenuation for the good dielectric will give you 0. Though there is a conductivity present, but due to this condition, the attenuation is very small, or you can avoid this and you can approximate to 0. Whereas beta is, again you have 1 plus 1 and you will get the same beta what you are getting in the for the lossless dielectric. So beta is equals to omega under root mu epsilon. Now, as alpha is 0, so you can have the propagation constant to be j beta. So this propagation constant will become j omega under root mu epsilon. Now the velocity, phase velocity is omega over beta. As this is a linear, beta is a linear function of omega. These two be cancel out, and again the phase velocity will only depending upon the medium, and it is independent to the frequency. So it will be constant, and there will be no dispersion. And again this eta equals to that, the intrinsic impedance is again becomes this one under root mu epsilon, and again this is a real quantity. So these will lead to same case when we have the lossless dielectric. So it is actually exactly not a lossless dielectric because you have a lossiness due to some conductivity, but when we impose this condition, due to this condition, this will exactly acting as a lossless dielectric. So, or you can say the losses are there, but they can be ignored. Alpha will be smaller and they can be ignored, and you can approximate to be 0 for general cases. And there will be dispersion that will, because we have approximated here, there will be dispersion, but that will be very small, and you can also approximate to be 0 here dispersion. And then the intrinsic impedance will also become almost real. There will be a complex quantity, but it will be approximated to the real. So these are the results for same as the lossless dielectric. Okay. Now, a special case, let's take the free space. We assume conductivity to be 0 and epsilon equals to epsilon naught and so on. So here it is 0 because conductivity is 0. So this will be a lossless dielectric. And for this case, just your alpha equal to 0, beta is omega under root mu naught epsilon naught. You can find the velocity. velocity is comes out to be 3 into 10 to the power 8 meter per second. It is a special case for the lossless dielectric, and the intrinsic impedance for the free space is 125. You can verify it. Now the electric field for the free space, instead of C, now we are writing E naught is the constant, so it is more effective to write the E naught. And the electric field, the solution of the wave equation is sort of like this. So let E equals to E naught cos omega t minus beta x ay. Let is the direction of the y axis, and it is we have just focus on the forward traveling wave. So in that case, H is comes to out to be H naught cos omega t, because the phenomena will remain same. The two things will change. This magnitude may change and this direction may change. Now because we have taken the AY and the wave is moving in the X direction, propagating in the X direction. So you have to take AX cross with the AY, that will give you the direction of the H. So AX cross AY will give you the AZ. So the direction of the AZ is perpendicular to the direction of the electric field, and now it will be AZ. It will be perpendicular to the both AX and AY and AZ. How to find H naught? We know that eta is equals to E over H. So eta was we have defined that EY over Hz component equals to eta. So you can use that Hz equals to Ey over eta naught. So just because this is a free space, we can put up eta to be eta naught, and you can find this to be E naught over H. If you know the electric field and if you know the intrinsic impedance, you can find the magnetic field as well. This is how. In general, if the electric field is not a direction of the y-axis but in a particular direction, for example, this is we have for example this three axis. This is one axis, and this is x, this is y, and this is z. So let's take the wave is propagating in this direction. This is the direction of wave propagation. So let's say that this is we denote with the AK direction. Now electric field will be perpendicular to this one. So let's have the electric field which is perpendicular to this one. So it will have some sort of, this will be let perpendicular some direction. So it will be, so we call to be the that A E vector, and this is your AK. Now the H vector will be perpendicular to both. So you can find that as we have find that in this case that you have AH equals to AX cross equals to AE. Yeah, we have find in this case that was AY, so we are getting AZ, and instead we have the AE. So we have taken the cross product of the direction of propagation with the direction of the electric field. Same case will be here. Now we have the AH which will be perpendicular to both, and we can have this one. So here this will be AH direction. So how to find the AH? So AH direction in general can be computed using the cross product of this direction of propagation into direction of electric field. Okay, so AK AE. So what you are getting? AK AE, and you are getting AH. So when you take cross product between these two, you will get this result. Plus, if you take AE cross this one, then this will give you AK. So it means direction of propagation you can find just by using AE cross AH. So if two direction is given, you can find the third direction. So either you can use this one. If direction of electric field and magnetic field is given, then you can find a direction of propagation. And if you have a direction of propagation is given, electric field is given, you can find the AH. Similarly, if AH and AK is given, how to find the AE? This depends upon you. You leave to you how to you will find it. So now focusing on these two in general, if A is the direction of electric field, A is the direction of magnetic field, and AK are the direction of the wave propagation or the unit vector along E field, H field. then AK cross AE equals to AH, or we can have a AE cross AH equals to AK. So this is, for example, this is the visualization of the EM field. So this is the direction of propagation, and E fields are in this direction, and Z H field will be in this direction. So you have this field. I have already shown the animation of this EM fields here. So if you, this is a YZ plane. If you have this YZ plane, it means the wave is propagating in the perpendicular direction of this page, this plane. And you have this E fields are here. They are varying in this direction along the y-axis, and H is along the z-axis, and wave is propagating in the x direction now, which is going inward perpendicular to this page. So if you rotate somehow, if this is the uh, E naught direction, then Z, this H will be here, and again this will be X direction. So you can visualize how it will look like. So here you have some conclusions. Both E and H fields called EM waves are everywhere normal to the direction of wave propagation. So everywhere, whatever the direction of propagation is, the E and H fields remain perpendicular to the direction of propagation. They form an EM wave that has no electromagnetic field component along the direction of propagation. So the E fields and H field don't have any component along the X. That's why they are perpendicular. If they have any component, they will not be perpendicular to the X. Such a wave is called a transverse electromagnetic waves or TEM waves. Though this is in the free space, these EM waves which are moving in the free space are called the transverse electromagnetic waves because the electromagnetic fields are transverse to the direction of propagation. Now it is called a uniform plane wave because E or H has the same magnitude throughout any. Now we will focus on why we call it to be a uniform plane wave, because we have defined that it is a plane wave, a wave which is varying in one direction. If varying, the electric field varying in one direction and independent to the two other direction. If you have two directions, uh, then this will be, if you vary along this direction, the electric field may change its direction or magnitude, as we have seen in this case. As we along this, the electric field, this is changing the direction. Here the direction is same, the magnitude is different. Here the direction is also reverse. The direction is changing in this here in X. Now for the, we have defined that when you move other two directions which are perpendicular to direction of propagation, the electric field remain constant. So if you have, for example, this is X, this is Y and Z, and we plot again this here. Now we have uh, this is, let this is y and this is z. So what it means that x will be perpendicular to this and the direction of propagation is the x-axis. Then if you move in this direction or in this direction, the electric field vector, whatever it is at this point, they will remain same. So what we'll see is that if you have electric field which is perpendicular, what we have seen here, which is perpendicular, here it is perpendicular, so it will be perpendicular. So when you move in this, it will remain same. It will remain same. It will remain same. So it will be constant in y-axis. Similarly, if you move in the z-axis, z direction, if this one vector, if you move at this point, this will have the same vector. It will have same. So it will be uniform in y and z. So if you have this plane, if you have this, we consider to be this plane. This page is a plane. So everywhere electric field will be constant. The direction and magnitude at every point on this plane will be constant. They will be uniform. Similarly, if you have a H field, for example, H field we have seen in this direction. So in the y direction, the H field are in this direction. So when you move in this y axis, it will be remain same magnitude and same. When you move the z along, it will remain same. Remain same in this plane, a particular value of x. So in this plane, H field will remain, whatever point you select, at same point the electric field and the magnetic field remain uniform, remain constant. So this plane is called the uniform plane. So there will be so many planes. One plane is there, another plane. So everywhere every plane will have a different electromagnetic field, but within that plane, that will have the same uniform. So if you have a, for example, you take this axis. So you have, so this is the direction of propagation. So this will have, let me draw the finite plane. So the cutting at this point. So here the electric field and magnetic field are here. So they will remain same. Another, we take another plane. Let's take this one. This time this plane, and here the electric field may be different. Maybe here and this may be some, this one E and H. So here the electric magnetic field are different from here, but within this plane they will remain same, uniform. And this plane is called the wave front. Generally we call these to be the wave fronts, which have the same value of the magnetic magnitude is same. Wavefront, those locus of point which has the same magnitude of the electric field, or the same magnitude of the magnetic field. So these are called the wavefront. So they are the wavefront which have a different wavefront. When you will pass the time, the wavefront will move because electric magnetic field will propagate this direction. So all which seems to be that this wavefront is moving, and so on. So that's why they are called the uniform plane wave, because in a plane perpendicular direction of propagation, the electromagnetic field remain uniform, remain constant. So that's why they are called the uniform plane wave. So as a has the same magnitude. And why we consider to be a uniform plane wave? Because when, for example, you have a point source, you have this one point source. So in this, for example, sun or similarly like this, if you point source, so wave will propagate in all direction. They will, EM will be generated. They will go, and everywhere the electric field magnetic will be perpendicular to here. So, so in this case, they will be spherical. Wavefront will be spherical. But as it spread outside, if a distance is very high, if this distance is very high, then you can see that at a distance, this curve become almost flat. So you can assume this portion to be a plane, not the curve. It's a constant plane. So uniform plane you can consider. That's why it is easier to understand a uniform plane, and we can approximate. So wavefront will be more towards the uniform plane. Now they are spherical in nature, and here you have a linear. So if the distance is very large, you can approximate the spherical nature into the linear nature here. That's why we are focusing on the uniform plane wave. Okay, so it is called a uniform plane wave because E or H has the same magnitude throughout any transverse plane defined by x equals to constant. The direction in which the electric field point is called the polarization of a TM wave. The direction. So, when, for example, if the electric field has the direction, if you have this one, uh, this is how the wave is propagating in this direction. So, this is the direction of the electric field. Then this called the polarization of the wave. Wave is polarized in this direction. So direction in which the electric field point is the polarization of the transverse electromagnetic waves. So the wave we have considered is polarized in the y direction. Till now we have taken this one. So this wave is polarized in the y direction. Direction is the y. Now same analysis can be done for any good dielectrics. We have focused on the free space. You can focus for the good dielectric. Only slide values will be different. Now next is the plane wave in a good conductor. So what is good conductor? When this factor is much greater than 1, then we'll consider to be a good conductor. That is sigma conductivity is much higher than this factor. In that case, the propagation constant is under root j omega mu sigma plus j omega e. Now you can approximate this value to be small because this is ratio is more than 1, so it can be approximate to the less than 1. So this will lead to 1. So you have gamma equals to under root j omega mu sigma, and this is under root j. So the phase of this is a 90 degree, and magnitude is this one. So this is a magnitude, this is the phase. When you take under root, then its magnitude will become under root this one, and phase will be half. So here sigma will comes out to be under root omega mu sigma under root 45. Now gamma is equal to 1 by root 2. Gamma equals to, now you can split into the real and image part because you want to find the alpha and beta. So you can put this r into cos 45, this is 1 by root 2 of this, and plus j into this into sine 45, j into sine. So this is the alpha is under root omega, this is alpha part, and this is the beta part. So the attenuation constant factor is this one, comes out to be pi f mu. This is very important, you have to remember is this one. So alpha is pi f mu sigma. So for good conductor its value become very high. Similarly beta will also be same, beta is under root, so beta and alpha are same here, and you have this factors. So for a good conductors, you have alpha and beta is to be high. Alpha is very high. F is very high, F is high frequency. Sigma is high for good conductor as compared to the F. So you will have the very high factor. In this case, the velocity of the wave in the conductor becomes omega over beta. And if you put up, so again, this is a function of omega. And you can say this value is, when you solve for particular frequency of this, its value is very small. It is order of the sound waves. So now the velocity will decrease, and also it is a function of omega. The two things are there. Now the velocity is depending upon the omega. What it means, it means dispersion will start. As of every signal, different frequency will travel with different phase, this phase velocity. So they will reach at different times. So signal will spread time leads to dispersion. So depending upon the frequency, it will lead to dispersion. Second thing, this factor is smaller as compared to free space velocity. So you will see it comes out of the order of the sound waves, or it may be around 500, 600 meter per second, depending upon the omega, and your typical value is around 500. So depending upon omega and sigma, this value. So velocity will decrease in much extent, and also it will become dispersion. So this is how the effect of the in good conductors. Second, the intrinsic impedance is given by this factor. When you put up here, when this factor is avoided, it will be 0. Then you will have here j omega sigma, and again it is, this phase is 45 degree. So you can have again eta equals to under root mu omega mu over sigma 45 degree here. So you have the phase of eta is 45 degree, and this is the magnitude of the intrinsic. So intrinsic impedance is complex, and also the propagation constant is also complex. Both are complex. Both have the same 45 degree. The propagation constant is have the phase 45 degree, and the eta is also have the 45 degree phase. Now to understand the electric and magnetic field here, so what we have already obtained, we have E equals to E naught e to the power minus alpha x cos omega t minus beta x, and some direction ay. So let's again, this is the direction of propagation, x is the direction of propagation, and here you have the direction of the electric field in the along the y-axis, and there you have the factor which is the attenuation factor, okay, E naught alpha. So if E is given, how to find the H? So you can, oh, this is a mistake here. You can can't directly find the H. So this is here. Just go from here to here. So this one, E is here. So we can find the phasor form. What is the phasor form of this one? The phasor form of this one will be the E naught. Now this is omega t minus beta x. So you can avoid this one. The phasor form will be the e to the power minus alpha x and e to the power minus j beta x. This will be the phasor form of this one. You can find it phasor form. So what you can find, you find the phasor form of H. So how to find the phasor form of H? You divide with the n naught here. So what we have done here, so H will be equals to, here this is the H vector. H will be equals to E naught over eta, e to the power minus alpha plus j beta. This is the phasor form, and you multiply it over j omega t. So this is whole factor divided with the real part. And we already know direction because direction of ax, this is the direction of the wave traveling ax, and ay, you can take the cross product, you will get the az. So we put up the az. So real part, now this is a complex. This n is complex. So we have to split into the real and imaginary part. So this is n, sorry, into the magnitude and the phase part. So this is a magnitude, and again it will be into the e to the power j theta n. So when you take it in the numerator, then it will be minus j theta n. So eta equals to n, magnitude of n, into e to the power j theta n. Now it will become e to the power minus j theta n. We will combine here. So when you combine, it will become e to the power minus alpha plus j beta plus j theta n into here. When you take this one real part, you will get this equation. So what you are getting? You are getting 45 minus omega t minus beta x minus 45 degree will be here, because theta n is there is 45 we have obtained. Then the phase of this n is 45 degree. So what you are getting, this is a theta n. So here you will get the theta n. This is a theta n. So for this particular case, it will be a 45 degree. So in this case, h is equals to e naught over magnitude. This is a real quantity. We assume e naught to be real. So e naught over this one will be the h naught. This will be the h naught, and attenuation factor is remains same, and now it will be cos omega t. So what will happen? You have now two things happen here. It will be divided by this one factor. There is a magnitude of eta, and here it will be now delayed by 45 degree. Previously, the E and H for the lossless have the same phenomena. They have the same variation. They are in the same phase. They have the direction is different, but this part is same. What we can say, they have the same phase. Now it is it is H is lagging by 45 degree. It is delayed by 45 degree. So this waveform have the same variation, but it will be out of phase with the E. Previously for the lossless or the good dielectric, they have the same phase. Uh, so here E leads H by 45 degree in good conductor. This is important. So they will be not in the same phase, but they will be offset, and they will be offset by 45 degree in good conductor. So this is an important result. Two, three things we have find. First, what we have find this one. You have the gamma with 45 degree phase. Alpha is very high. Attenuation is very high. When you put up for typical values, you will get very high values. Then velocity is depending upon the omega, which give you dispersion, and also its value very small as compared to the free space. And eta, the interesting impedance, is also complex, but now the phase is 45 degree. And second, H is lags by E by 45 degree. Now they are out of phase. E and H have not have the same phase, but will be out of phase in the good conductors. So what we have concluded here. So good conductor gamma is very large and alpha beta are also large. The wave is attenuated greatly as it progresses through the conductor because alpha is very high. The velocity of the wave, being inversely proportional to beta, is very small in a good conductor. So because beta is very high, so we can say the velocity will also. So what we can see is the same order of magnitude as that of a sound wave in air. So this is an important conclusion for the good conductors, where the ratio sigma over omega epsilon is very high. Okay. So next we will start a depth of penetration. I stop it here.